All right, now we're going to go over additional examples on stress due to bending. This is the lecture that would normally take place on a Thursday, where we just solve more problems using the material we learned. So there's only three problems. The first one says that there's a beam that's constructed from 4 pieces of wood. They're all glued together as shown. So it's like this little square here. It's a square beam. It's hollow. The maximum moment is equal to 10 kip feet. So I gave that to you, so you don't have to do a shear moment diagram. Determine the maximum bending stress in the beam and determine the bending stress at the inner wall of the beam. So the maximum and at the inner wall. So we need to use this equation, sigma max equals mc over I again. We know m is given to us as 10 kips feet. C is 10 divided by 2. I get 10 from the overall height here is 8 plus 1 plus 1. So 8 plus 2 is 10. So 10 divided by 2 is 5. Okay, but we don't know is the moment of inertia. So you still have to solve that. And that is going to be the total is equal to the big square, which I'm calling like the outer square, minus the small square, which would be the inner square. And we don't need the parallel axis theorem because they both share a centroid, okay? Because it's symmetrical, we could see that. So they both share a centroid, so their y squiggles are going to be the same as the y bar. So we don't need the parallel axis theorem, so we could just subtract them. Okay, they're both relative squares, okay? So they're, even though I'm calling a big square and small square, they're actually technically rectangles, but we're just going to do Ix of the big square, which is 8 inches. Its base is 8 inches, which is 6 plus 1 plus 1, times 10 inches, which is the height again, cubed divided by 12. I get the devil's number. Then I do the small square, which is 6. It's just 6 inches from here, and its height is 8 inches. Cube that divided by 12, I get 256. Then I could just subtract the 2. It is 666.67 minus 256 equals 410.67. That's the total bending. Oh my god, that is the moment of inertia. The total moment of inertia. Okay, then I can just plug that stuff in. I know the m, I know the c, I know the I. So 10 kip per feet. Okay, well that's in feet. Everything else is in inches. So I need to multiply that by 12 inches per foot to get the foot away. Multiply by 5, which is c, divided by 410.67 inches to the fourth. That's equal to 1.46 kips. We have kips here. Kips over inches squared is KSI. That's the maximum. So that's one of the answers. Okay, but what about the inner wall stuff? Well, the inner wall, I'm talking about, like, there's actually a little dot here you can kind of see, which is just right along, like, where it's glued. Okay, why the heck would I care about that? Well, because like I just said, that's where it's glued. And a designer would want to know if they have sufficient glue to withstand that this stress here. So if typical like Elmer's wood glue might not be sufficient if there's a huge moment of 10,000 pounds per foot on this thing. So you might need to get a special glue to withstand that. So a designer would probably want to know what that stress is at that specific point. Well, it's going to be real close to the 1.46. So, but we want to know exactly what it is. So we're going to use the my over I equation, okay, which is just we still use the 10 kip feet. We need to put that into 12 inches. Well, the distance from here to there, well, it's 8 inches, the total distance. Well, that's just divided by 2. Then we're still going to divide by the same I. And it looks like I forgot to write the answer here, but I'll do that real quick. It's 10 times 12 times 4 divided by the 410.67. Okay, do that, and I get 1.16 kips per square inch. Okay, so this answer is 1.16 kips per square inch. Like I said, it's going to be real close to that, but smaller. But we want to know what the exact number is because we want to specify a type of glue to hold that in place. Okay, and even if you nailed it, you want to know if the nails could withstand that shearing force there. That's gonna be there, caused by this this stress due to bending. Okay, that's it for this problem. Again, this answer is 1.16 kips per square inch. All right, so that's problem 1. Problem 2 is similar, but it's not a full box. Okay, we take the bottom part off. Okay, so it's maybe like a chair or a stool looking type thing. It's made from 3 boards. These ones are nailed together instead of the glue, but that mechanism doesn't 100% matter in our case. Okay, it's just what the designer would care about. If the moment acting on the cross section is a maximum moment of 600 Newton meters, it's actually drawn here. You can see it's 600 Newton meters. Determine the maximum bending stress in the beam and the minimum bending stress in the beam. Okay. I actually don't even think I saw for that minimum part. Doesn't matter too much. Okay, but first we need to find the y bar. Okay, let's just find this y bar. So because the centroid is not just like convenient on this one. Okay, this one is all symmetrical, so the centroid was in the middle. Okay, but this one is not, so we have to figure that out. So area of the side. Okay, the area, I'm just calling this little piece a side, and this is a top. So area of a side, those are symmetrical, so I only need to do this calculation once. 20 millimeters is the base. Its height is 150 millimeters. Okay, so that would be 3,000 millimeters squared. The area of the top, 240 is its base, which is 200 is from here to here, but each leg is 20, so 200 plus 20 plus 20 is 240. Its thickness is 25 millimeters. That gets me 6,000 millimeters squared for the area. Total area is 2 times the sides plus the 6,000 millimeters squared is 12,000 millimeters squared. Okay, now I need the little squiggles, the y squiggle, and I'm measuring it from the base right here. I've drawn like a little X as my little measurement location. Okay, for the side, this is a square, a rectangle, so it's 150 divided by 2, so that's 75. For the top, and 150 gets me to this interface, and then it's a rectangle, so 25 divided by 2, so 150 plus 25 divided by 2 is equal to 162.5 millimeters. Then I plug that into the y bar equation. Okay, 2 times the side pieces, so 3,000 millimeters squared times 75, okay, because there's 2 side pieces, plus 6,000 millimeters squared for the top times the y squiggle for the top, divided by the total, gets me 118.75 measured from the x-axis. Okay, so that's where that is, 118.75. You could also do a big square minus the small square. That works too. Just be consistent with your measurements. Okay, so now I need to get the moment of inertias. Because the y squiggles are not the same as the y bar, you need the parallel axis theorem. So I'm doing the moment of inertia of one of the sides regarding the x-axis. Okay, base height cubed here, 20 millimeters, 150 millimeters cubed over 12, plus the area, 30,000 millimeters squared, multiplied by, okay, the distance, the d, which here is y bar minus y squiggle for the respective one. So y squiggle for the side is 75. So 118 minus 75, square that. Do all the math, I get 101.14 times 10 to the 7th millimeters to the 4th. For the top, base height cubed again, but the base is the long side, so 240 times 25 cubed over 12, plus the area, 6,000. Okay, we need to get that distance. Okay, it's 162 minus 118. Okay, this time it's y squiggle minus y bar. Again, from the lecture, it doesn't matter. I always put the bigger number first because I want a positive number. If you're always consistent, it's not going to matter because you're squaring it anyways. Okay, it's just a habit of mine if you're wondering. Okay, but that gets me 1.17 times 10 to the 7th. Then I just add them all up, but I need 2 times the side, the 114, twice that, plus the one top. I get 3.45 times 10 to the 7th millimeters to the 4th. Okay, then the max is mc over I, that equation that we always need. M is 600 Newton meters. C is just y bar, which we just got, 118.75 millimeters. Okay, then I plug it all into the equation. 600 Newton meters times C, okay, which is just y bar, okay, 0.118 divided by the 34.5 times 10 to the negative 6. I needed to convert this because previously I got all this answers in millimeters to the 4th. So I converted that to meters to the 4th by multiplying this number by 1 over 1,000 4 times. Okay, because we're meters to the 4th. I do that, Okay, we're in newtons over meter squared is a pascal, so 2,052,173.9 pascals, which is 2.05 megapascals. Okay, so that is the overall maximum. Okay, so y bar would get me to the maximum, just like we did in the first problem in this lecture. Y bar wound up getting me to the maximum because that's the furthest distance from the centroid to the outer fiber. Okay, now I don't have written on here, but this problem also asked for the minimum bending stress, like the non-zero one, because it's 0 here, whatever that centroid is. But to do that, you just use this other shorter distance here from the outer edge. That's what I was asking, because overall the maximum is occurring here at the bottom, because y bar is from the centroid out here. But the minimum would just be this mc over I again, but we're using y this time. So still 600 Newton meters, okay, times y changes. And y is going to be, I can actually do it here in my calculator next to me. I would do 600 Newton meters. My y would be this overall height, 150 plus 25, which is 175. So 175 minus y bar. That would be this remaining distance from here to here. And y bar is 118.75. So right now I have my calculator. 600 Newton meters times 175 minus 118.75. Okay, that gets me the location from here to here. So that's my numerator. And then now I'm going to divide the 34.5 times 10 to the negative 6. And I'm still getting pascals. Okay, but I get, let me see my calculator. I get 978,269. So it'd be 0.9 megapascals. Okay, or 978 kilopascals. Okay, so it's definitely less than that, okay, because that distance is smaller. Okay, so that's what I wound up getting for the smallest one. All right, so then let's move on to this next one. Okay, a steel beam carries this load as shown in the figure. The loading is to be applied strictly from this laboratory testing. Okay, so the base is rectangular with a base, the beam is rectangular with a base of 4 inches and a height of 6 inches. And I want to specify a suitable steel for the beam. So 800 pound per feet distributed load, 800 pound per feet distributed load here. Cantilever beam, okay, it's the same problem that we saw in the shear moment diagram lecture. Okay, we're going to use ultimately the sigma equals mc over I equation. But we need the shear moment diagram, but there's a sort of trick with a cantilever beam. The maximum always is at the support condition, okay? Because there's nothing over here, so moment has to be maximum over here and go down to 0 over here. So just knowing that trick, I don't need to do a shear moment diagram, but I do need to figure out what that moment is right here. Okay, sigma equals ma equals ma needs to be written here. Okay, it's not, I didn't draw it here, but there's an unknown right here, moment, minus 800 pound feet, that's the magnitude of this distributed load, times 8 feet. Okay, that gets this into a resultant force that's not drawn here, but it's right here, and it acts at a distance half of 8 feet, which is 4. Same thing here, 800 pound feet multiplied by 8 feet gets me a resultant force here, and its distance back to A is 8 plus 4 is 12. I do that math, and I get MA is 51,200 pound feet. Okay, but it's in the opposite direction than I assumed. Okay, when I did this math, MA is positive right here. So MA must be counterclockwise. Okay, so that's what I've assumed. This answer comes out MA is equal to negative 51,200 pound feet. So this load goes the other direction. Okay, for the sake of these types of problems, this doesn't matter as long as you get this number right. Okay, so from that same table that we've always been using, we see that's a static load. It's a steel, which is ductile, so the sigma D, the design, is equal to SY over 2. Okay, I rearrange the equation, so therefore SY is equal to twice the sigma design. Okay, because we're ultimately trying to find a suitable steel. So I need to find something that's twice the design strength, the yield strength that's twice the design strength. Okay, so sigma D is still equal to MC over I. MA is the 51,200 pound feet. C is 6 divided by 2. I'll get that, the dimension. The height is 6 inches. Divided by 2 is 3 inches. Okay, the moment of inertia is 4 times 6 cubed over 12. Gives me 72 inches to the fourth. And so then I plug all that in. 51,200 pound feet. Okay, we're in feet, so I need to convert that to inches. So be careful, because everything else is in inches. So multiply that by 12 inches per foot times C divided by I equals 25,600 psi, or 25.6 ksi. Okay, I converted that to ksi. We know that Sy needs to be twice that, which is 51.2 ksi. So now go to table A10 and pick a steel type with a Sy that is slightly higher than 51.2 ksi. Okay, so just go back to that table that's in that lecture, and we see that 1080 annealed has an Sy equal to 54 ksi. So this one's just slightly above it. It's perfect, so that one's okay. So that's a suitable one. Okay, you might be wondering if, like in exams or whatever, people could choose different ones and it'd still be acceptable. I ideally want the one that's closest to it, slightly above it, but I will be willing to accept a few other options that are slightly higher than that, but not overly so. Okay, it's sort of going to be at my discretion this, but try to get it as close as possible to this, equal to, or slightly higher than it, maybe within like plus 10%, something like that. Okay, but that's how you would choose and solve these problems where you select the steel. Okay, that's it for the example problems. We're just using this MC over I equation. We just need to get M and I are probably the biggest issues in these problems. But that's it.